myself Dr. J D Kalyani, working as Associate Professor in the Department of Computer Science and Engineering of Institute of Aeronautical Engineering. In this video, I will discuss about CPU organization. At the end of this video, the student will able to understand what are the structural elements of the CPU and how they are interconnected, what are the basic functionality of various internal components of the CPU. The basic agenda of this video is abstract view of CPU, ALU, bus organization, basic CPU organization, types of CPU organization. So, here the structural elements of CPU, how they are interconnected with the bus organization, what are various varieties of CPU organization will be discussed in this video. As an introduction, from the functional units of the computer, the block diagram consists of three major units. The one is input unit, second one is central processing unit. In short, we refer it as CPU, and the third one is output unit. The input unit provides the human-computer interaction. The user can supply the need data for processing to the system with the help of input unit, and this has to be supplied to the CPU with a human computer readable form. So here, whatever data programs that are supplied by the user can be stored in the main memory. The CPU majorly consists of three subunits. One is ALU, control unit, and the memory unit. So while taking the top level or abstract view of the central processing unit, so here the user has to be interacted with the CPU with the help of input devices. Whatever the data or information that is produced as a result of processing has to be represented by using the output devices. So input-output devices has to be interaction with the central processing unit, and the data, values and intermediate results that are produced in the processing can be stored in the main memory. So the interconnection of all these has to be done with a bus organization. So the top level structure of the CPU majorly can be viewed like this. Now we can explore the central processing unit. In the central processing unit, the internal components are majorly the registers, next arithmetic and logical unit, and the control unit. These units has to be interconnected with the bus organization. So registers are very small sized and has to be very high speed and are available within the processor. So various registers we have discussed in the last videos, like instruction register IR and program counter PC, and various general purpose registers can be accommodated on the processor. So central processing unit majorly performs the data processing operation and also stores the information in the main memory, and it can produce the control signals in order to coordinate and monitor various units of the computer with the help of control unit. So the CPU module can take the basic interactions like this. The CPU can receive instructions, data, or interrupt signals. So these can be supplied with the CPU. Instructions has to be supplied through programs, and what is the needed data that a program has to be operated, and the another variety is the interrupt signal. Interrupts are the signals which can stop the program execution temporarily. Then the CPU has to shift to the interrupt service routine. So ISR program has to be loaded and can be executed. After completion of execution of ISR, the suspended program may resume into the execution. So by using the interrupt signal, the current program execution can has to be suspended. So CPU can has to receive either the instructions, data or interrupt signals. So it can store and it can read and write from the memory. So it requires the address as well as data. That what data has to be written into the memory can be derived by the data, and at which location in the memory this data can has to be performed, the operation can be pointed by the address, and which operation either to perform the read operation or the write operation, those control signals can has to be generated. So the CPU module can receive instructions, data, interrupt signals, and it can issue the address data to activate the memory based on that control signal, what operation is to be carried out on the memory. So the subsystems involved in the central processing unit is the control unit. The control unit majorly performs the coordination of various units that are functioned in order to execute the program successfully. So this coordination can be achieved with the help of clock signals. Next subunit of the central processing unit is the arithmetic and logical unit. The basic arithmetic operations like addition, subtraction, multiplication, division, and the logical operations like and or not are carried out with the help of arithmetic and logical unit. How these operations can be performed with the help of arithmetic and logical unit can be illustrated with this circuit. So here this is the ALU. The ALU can receive two operands as input, A and B, and here applies the operation, and whatever the result that is produced can be stored in the C. So here C is equal to A operand B. This operation can has to be specified with this circuit. The control lines can has to be used for specifying the operation. ALU basically performs 4 arithmetic operations: addition, subtraction, multiplication and division, and 4 logical operations. The 4 logical operations are and, are, not and exclusive are. So in order to support these operations, 3 control lines, 2 power 3, 8. So 8 operations we are performing. So 3 control lines can has to be needed to perform these basic arithmetic and logical operations. So those control lines can has to be denoted with C0, C1 and C2. So here when the C2 value is 0, the ALU can perform arithmetic operations. When C2 value is equal to 1, the ALU can perform the logical operations. So when C2 is equal to 0, depending upon the C0 and C1 control lines input, the basic arithmetic operations can be performed. When the C0 0, C1 0, then addition operation can be performed. When the control units C0 and C1 1 0, then subtraction can be performed. Next, when the C0 holds 0 and C1 holds 1, multiplication operation can be performed. When both inputs are 1 for C0 and C1, division operation can be performed. In this way, the basic arithmetic operations can be performed by the ALU. And not only the arithmetic operation, the logical operations that can be supported for the ALU are and, are, not and exclusive are. When control unit 2 is 1, then the ALU can perform the logical operations. And depending upon the control lines C0 and C1, the logical operations can be performed. When the C0, C1 both are 0, or logical operation can be performed on the operands A and B. And when C1, C0 is 0, 1, and operation can be performed. And when C1, C0 is 1, 0, NOT operation is performed. When both the values are 1, exclusive OR operation can be performed. So in this way, the ALU can perform both arithmetic as well as logical operations. So what the two numbers can has to be supplied with the two resistors A and B. The operation can be selected via the control lines depending upon this truth table. And after applying the operation, what is the result that are generated can be stored in the another register C. So C is equal to A operation B. So in this way, the arithmetic and logical unit performs the basic computational processing of the instruction. Not only these arithmetic logical unit registers, the interconnections can has to be done in the CPU with the help of bus interconnection. The layout of the bus can be like this. A bus is a communication pathway between the two major components of the computer. So there is a number of possible interconnection systems. Single bus system and multi-bus system can also be there. So here, when more devices are connected with a bus organization, it has to increase the load so that the speed of processing can be greatly reduced. So to avoid this, single bus organization can has to be shifted into multi-bus architecture. What are the various multiple bus hierarchies? There are three varieties of multiple bus hierarchies. The first one is traditional hierarchical bus architecture. The second one is high performance hierarchical bus architecture. Third one is PCI, desktop and server system architecture. So these are the three multiple bus hierarchies. The first one is traditional hierarchical bus architecture. So here the local bus can has to be used in the traditional hierarchical bus architecture. So this, by using this local bus, the cache or the memory can be insulated from the processor. So here the memory can has to be connected with the system bus, and here the cache can be directly connected with the processor with the local bus. So here the use of cache structure insulates CPU from the frequent access to the main memory. So main memory can be moved off to the local bus to the system bus. Main memory is connected to the system bus. So here the buffer transfers, data transfers can has to be made with the expansional bus. The devices that are involved in the demand of communication can has to be connected with the expansion bus. So memory to processor traffic can has to be greatly reduced, and the memory can be directly connected to the system bus. So traffic, IO traffic can has to be taken care by the memory with the help of expansion bus. This type of architecture is called traditional hierarchical bus architecture. The next type of bus architecture is high performance hierarchical bus architecture. So here a bridge has to be installed. So this bridge has to be act as an interface between the buses. The local bus and the system bus can has to be connected via the bridge. So here also, in order to improve the performance and speed of accessing the IO, these hierarchical bus structure can be used. Generally, the processor component and the computer components are electronic devices, but the input-output devices are electromagnetic devices. So here the speed of IO devices can has to be synchronized with the speed of processor. So this can be achieved by installing hierarchical bus architectures. So high speed bus can be used for IO devices that involves in high rate of IO traffic. Next, the CPU can has to be insulated from the main memory by frequently requiring accessing and fetching instructions from the main memory. So the cache has to be connected with the local bus and the main memory can be connected with the system bus. The interface can be between the local bus and system bus can be the bridge. So in this way, the traffic of the speed synchronization between the I/O devices and the memory can be maintained in the high performance hierarchical bus architecture. Next is PCI desktop. So peripheral component interconnect is the full form of PCI. So here the PCI is the PCI bus. In this, various I/O devices can has to be connected with the expansion bus in order to take care of more demand I/O traffic, and the bridges can has to be used in order to take care about the memory cache and the processor access. So here the speed synchronization, and here the buses can act as input output processor for synchronization or mismatch of speeds between the I/O devices and the processor. So this is another way of PCI server. So here host bridges are used in order to monitor the local I/O traffic demands. So the host bridge 1, host bridge 2, two bridges has to be used to monitor the I/O traffic, and this can has to be host bridges can be connected to the system bus in order to establish the communication pathway between the cache, main memory and the processor. So this is the PCI server connected bus. So all these are varieties of interconnection by using the multiple bus architecture. If a single bus is used, all devices are connected to this bus. So arbitration mechanism can be difficult, and the speed of processing and accessing information can also be greatly reduced. That's why these multiple bus architectures are more useful in order to connect high traffic devices to one bus and low traffic devices to other bus, and the arbitration mechanism can be also reduce the complexity in case of multiple bus architectures. Coming to next slide, that is the CPU, basic CPU organization. So here this is the memory unit. Memory can be viewed as a continuous storage cells like an array. So each cell can has to be uniquely assigned a memory address. And this is the central processing unit. The central processing unit and the memory can be connected with the outside bus. The system bus can has the three internal buses. They are the address bus, data bus and the control bus. The control bus can has to generate the control signals. Those are the read or write signals. Depending upon that, the control bus can activate the either the memory read or memory write operations. And within the CPU, one more internal bus is there in order to connect the internal parts of the central processing unit. In the CPU, we are having the general registers and the ALU. In the ALU, we are having the input register 1, input register 2. The ALU perform the 8 basic arithmetic and logical operations, whatever just now we discussed, and the result can be stored in the output register. And not only this memory, ALU, the another subunit of central processing unit is the control unit. So the control unit can be connected with the instruction register and the program counter. These are the two special registers that are used for program execution. The instruction register can contain the address of the current instruction that is being executed by the CPU. The program counter holds the address of the next instruction that can be taken by the CPU for execution. So here instruction decoder, the decoder can be used during instruction cycle. We are having a decoder part. So the decoding phase can has to be executed with the help of instruction decoder, and the control signals, the read-write control signals can be generated by the control unit. So when, for example, if you take, we are having a 3 lines of program, and here the current instruction that is being executed by the CPU is the first instruction. So the address of this instruction can be loaded in the instruction register, and the address of next instruction being executed can be loaded in the program counter. So the second instruction address can be loaded in the program counter. So after this instruction has to be fetched, it has to be decoded, so that what is the operation that is going to be executed on the instruction can be taken care by the ALU. Whether it is a arithmetic instruction or logical instruction, that has to be taken care by the ALU in order to process that instruction. So later on, after completion of execution of this instruction, the IR has to move to the PC value has to be moved to the IR, and PC can be pointed to the next instruction. So like this, the sequence of instructions has to be executed with the help of this basic CPU organization. So the major subcomponents of the CPU are the memory. So the memory has to be accessed and connected with the external system bus with the internal components of the control unit, ALU, and the register with the internal bus. So this is the basic CPU organization. So in order to increase the speed of execution of the program and to improve the throughput of the program, that is number of instructions executed per second, is generally referred as throughput. In order to increase the throughput, parallel execution of the program instructions can be considered. So how these parallelism or simultaneous execution of instructions can be achieved means with the help of multiple CPU organizations. Those organizations we will discuss next slides. What are the basic CPU organizations? We have to discuss. The basic CPU organizations are General Register Organization, Single Accumulator Organization, Stack Organization. General Register Organization, generally the registers has to be used. How data has to be supplied to the ALU while performing the processing, depending upon the 3 types of CPU organizations can be classified. So the first name indicates that general register organization, general purpose registers can hold the operands of the arithmetic operation in case of general register organization. The second one is single accumulator organization. So in this type of organization, one operand can be stored in the accumulator. The second operand can be supplied with the help of the general purpose register. So that type of architecture is called single accumulator organization. The third one is stack organization. Here the operands for the arithmetic operation can be stored in the stack, and the basic operations that can be applied on the stack is push and pop. Whenever an operand has to be placed in the stack, push operation can be applied and it can be retrieved from the stack. Pop operation can be applied. So the operands can be stored in the stack in case of stack organization. The first type of organization is register based CPU organization. So here the CPU general purpose registers can be used in order to store the operands of the arithmetic operations. So here, for example, register general purpose register R1 can hold the first number. If you want to perform addition of two numbers, the first number has to be stored in the R1 and the second number can be stored in the R2. And we can apply the arithmetic operation add R1 comma R2. So the operands are stored in the registers. So first number, second number can be added and the sum is stored in the register R1. So for example, it is a 3 address instruction. 3 operands can be specified. So in this case, we can store add R3, comma, R1, comma, R2. So the two numbers, first number, second number can be added and the result sum can be stored in the R3. Like this, the general purpose registers can be used to store the operand and the result so that the user can easily perform the processing and can easily perform the representation of assembly language instructions in case of register-based CPU organization. The next one is single accumulator organization. So in this, one of the operand has to be stored in the accumulator. The next operand can be supplied with the help of general purpose registers. So if you observe that here the arithmetic and logical unit, the accumulator can be the register that is connected. So one operand can be stored in the accumulator and this is the data register that can hold the another operator. For example, two numbers if you want to add in this type of organization. So here these type of CPU organization generally use single address instructions. So first the first number has to be stored in the R1 and we have to this register has to be load the first operand, first number. First we have to load to the move the first number to the accumulator. So the accumulator has to be contain the values. First number is moved to the accumulator and we can add directly the second number that is stored in the R2. First number is holded in the accumulator and we are performing the addition operation with one operand in the accumulator and the second number is in R2. And again the sum is stored in the accumulator only. So this type of architecture, generally the assembly language instructions can be used the accumulator as one operand during the arithmetic instruction processing. Next is the stack organization. Here the operands has to be stored in the stack. So we can use push and pop operations in order to insert the operand in the stack and to retrieve the operands from the stack. For example, if you want to add two numbers, the first we have to push these numbers into the stack. So by using two push operations, these operations can be pushed and if you want to retrieve them, then pop. Those has to be stored in these two latches. Next, we can simply perform the add operation. So here this type of instructions we generally call it as zero address instructions. So we are not specifying any operands. Those operands are readily available in the stack and can be popped to the latches in order to perform the arithmetic and logical operations. So this type of architecture is called stack-based CPU organization. So these are the three basic CPU organization which can be used to support zero address instruction, one address instruction, two address and three address instructions of the assembly language. Generally, the zero address instructions can be supported with the stack-based CPU organization. One address instruction can be supported with the accumulator CPU organization. 2 and 3 address instructions can be supported with the register-based organization. In order to increase the throughput, the number of instructions that can be executed per unit of time has to be improved by using the multiple instructions can be simultaneously executed. So this has to be achieved with the multiple CPUs. So here a program is generally can be considered as a collection of instructions. So the number of instructions, so this has to be measured in instructions per program. How many number of instructions per a program. So the average instruction, how it can be executed, the each instruction can be executed and how many number of cycles can be taken per each instruction can be measured as CPI, cycles per instruction. So this is per instruction. Next, the CPU has a fixed clock cycles time. So that is the clock rate. So that can be measured in seconds or cycles. So here CPU execution time is the product of the above 3 parameters. So seconds per program, instructions per program into cycles per instruction into seconds per cycle. So this is the number of instructions per program. Each instruction how many cycles are taken and what are the CPU clock rate, the seconds per cycle. With this the CPU time can be assessed. So in order to improve the CPU performance, we have to decrease the clock cycles per instruction and decrease the clock time and also decrease the number of required cycles and improve the architecture, ISA architecture or the compiler. So in order to improve the performance, multiple processor or parallel architectures can be considered. So in these multi-processor systems, more than one CPU can be available. So this is the first variety of architecture in the multi-processor architecture. So here more than one CPU, 4 CPUs are available, but these CPUs can be shared the common memory. And in the second variety of architecture, the CPUs can have their individual memory and they can share the common memory. So in this parallel processing, some data can be maintained commonly in order to execute the instructions parallelly. That data can be stored in the shared memory and CPU individual processing data has to be accessed from the individual memories. So like this, more than one processor has to be connected for the simultaneous execution of the program in order to improve the throughput of the computer. And multi-core processors also, here we are having not only a single core processor, in multi-core processors also more CPUs having their individual memory and can be connected with a shared memory via bus interface has to be connected with the off-chip components, the IO devices. So by using these core processors, we have to improve the number of instructions that can be executed per second. The throughput and speed of instruction execution can also be improved. So in this video, we discussed about the basic CPU organization. So what is the abstract view of the CPU? What are the major internal components of the CPU and how the interconnection between these components can be carried out with the bus organization and how to move from a single bus architecture to the multiple bus architectures and what are various multiple bus architectures. Next, what are the varieties of CPU organizations? How the general register organization supports the 2 address instructions and 3 address instructions, and how the accumulator architecture can support a single address instructions of the assembly language, and how the stack organization can support the 0 address instructions of the assembly language. How the CPU clock time can has to be measured, and what are the parameters can be considered in order to improve the CPU performance, and how multi-core processors can be used for parallel execution of the instructions. So this is about the basic organization of the CPU. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.